Okay, hi everyone. Welcome to OpenCV Workshop Part 2. In the previous weeks, we've covered a bit on about how we're gonna make use of histograms to kind of analyze images in terms of their different color scales. And we've also looked at making use of track bars to kind of isolate certain colors and colors that we want to detect specifically in our world lah, because our world is made of many colors, so we want to isolate certain colors. And in today's session, we're gonna see how we can make use of color detection to isolate objects using certain colors. So what you guys will be learning for the first part would be making use of masks to kind of isolate colors, as well as a bit on functional programming. So to start off, let's say I have this image of Singapore over here. You realize that if I were to isolate the red parts only, because the Singapore flag is really only made out of two colors, it's isolated very well. You will see one part, say the top part over here. Okay, this is not Singapore flag, but yeah, you get the point. So you'll see this top part over here, which is isolated with white, and then the rest is all black. So this tells you that the colors are very distinct. But if the colors were to be less distinct, if there was, say, a mirror of colors in let's say your typical house, there's a lot of colors, you know, isolate a certain color, how are we going to do that? So today we're going to make use of this thing. So before we start off and we draw like find a way to isolate the colors with the bounding box kind of thing, what we're going to do is how we're going to implement this method lah. So the first thing you do is you first capture information through your webcam on your laptop. So I'm giving you guys this overview of how your Python program will run. So the first up, we're going to capture information using a webcam. So probably either your external or internal webcam, you'll need to specify that. Then after that, we will use a mask to kind of set the lower as well as the upper boundaries for the colors that we want. Once you have the mask of like different colors of the specific color that you want, say red color, we're going to make use of a CV2 function known as find contours to kind of separate the larger contours by the area. So what this will mean is, because let's say if my house had multiple red objects, and let's say if I only really wanted the biggest object in the image, say a hole puncher, or I don't know, a book. So then by definition, what we will do instead is we will make use of we'll sort the array into a descending order so that we will be able to get the largest contours. So that's what we'll do this over here in the fourth step. And lastly, we'll draw a rectangle around the sorted the contours to view the finished product. So it's pretty similar to how, you know, previously, if you all saw in the previous at the start over here, in the Tesla car, where is it? In the Tesla car over here, you managed to isolate like certain objects, right? Yeah, so that's kind of like a final product. Except instead of recognizing that this is a color, we will recognize it according to a certain color that we want. Okay, so we already have a Python program that we have already preset for this. So what I need you guys to do is go over to your file system, like your file explorer, sorry. Okay, so mine is over here. So your file explorer over here. And I'll need you guys to go down to wherever your files have been stored lah. So if it's stored in your downloads or whatever, go and open it up. Yeah. And you open up your whatever your file name is called, you go back to your lesson files, and you will see this worksheet over here called color detection.py. Then you open it. Okay, then once it's done opening, somewhere here, yeah. Okay, so once you are done opening up the page, you should see something like this. So there's some blanks for you guys to fill in. Okay, so the first thing is, once you have opened up this page, you need to import your CV2 library. So import CV2. And we'll also be making use of the NumPy library. Are we? Yeah. Yes. So we'll make use of the NumPy library later. So import NumPy as NP. So NumPy library, if you are still not aware, is basically my library with like certain math like functions as well as things to manage data lah. So that's NumPy is for. Yeah. Then I'll be using my laptop webcam, so I'll set 0 as my to choose my internal laptop webcam. Okay, then once I'm done with that, what I need to do is I'll need to kind of read the images from the webcam. So how am I gonna do that? I'll make use of a while true loop. So while true will kind of continue forever lah. Yeah. So make sure you make use of a while true loop. Then after that, I'll read from a capture. So the capture over here, what it does is it comes up with two values. So I think the other two have covered it again, but I'll just recap. So for the capture function, what it does is basically returns some value that's not actually very important for like our purposes today, so we won't really cover that. And the second one is the frame, which is important because it's basically the values of the image that's being read out from the camera. So I'll just call it a retrieval and frame. Then after that, because HSV is kind of the more efficient like color space that is more efficient than BGR for processing, we will need to convert the default image from BGR to HSV. So we'll first specify the frame that we want to convert, which is the same variable over here. And then we will convert cv2.color. Then underscore the BGR to HSV. Then after that, we'll need to set a certain range for our colors. So we'll first set a lower bound for our color. So a lower bound. I'll just create a variable called low rate. You can call it anything you want, but just make sure to specify it in the other arguments later. Low rate, which is a NumPy array over here. Then I'll also create a higher bound. NumPy.array. Okay, so of course, this array cannot just be an empty array. It has to take in some values of some sort lah. So where are we going to get the values to kind of know what's the color what's the suitable color for this? So to do that, what we're going to do is we're going to make use of the trackbar application that we created previously. So if you go back to your folder over here, if you have your trackbar, which is called GUICV2 worksheet, you open it up, you will see the worksheet over here, which was taught last week by Zhe Zhao. So what I want you guys to do is go ahead and run the worksheet. And if it works, which it should, you will see the trackbar. Wait, let me try and bring it up. You will see the trackbar over here. So I have a color over here that I want to isolate, which is this red color over here. So what I'm going to do is I'm going to adjust the HSV values to kind of isolate this color. So give me a moment. Okay, yeah, my lighting conditions aren't very good, but the basic. Okay. So I think I've sort of isolated this image pretty okay. So if once I'm done with this color, I'll make sure to keep track of this color. And I'll go back to my other worksheet over there in the color detection worksheet. My color detection worksheet, I'll make sure to fill it up with the respective colors. So wait, so my colors were 116 to 179. So I'll set the lower rate. I'll create the array 116, then 116, 120 and 25. Then I'll create another numpy array for this, which is okay. Then that's the values that I'll be using. For you, it might be different. So just try out and figure out your values for your low array and array. Okay, I'll pause for a moment. Do you have any questions at this point in time? Once I'm done with setting a low and a higher array, what I need to do next is I'll need to make use of the inRange function to kind of isolate the colors lah. Input the lower and the higher boundaries. So low, high. So this will be the lower boundaries and the higher boundaries. And we need to find the contours from the image. So over here in the find contours, it takes in multiple parameters. There's a few different like algorithms that are preset that you can kind of choose which one you want to kind of find the contours. So there's the external, which takes out all of the, which kind of like retrieves all of the extreme outer contours. You know, like in the image. Let's say if you were to highlight it, like you did a outline of an image, then there's be the inner and the outer one, right? So what this external one does, it just takes the outermost circle. Then the list just gives you like the even if they're found like one in another, basically it returns you all of the possible contours. This is the third one, the CCOMP, is basically it gives you all of the contours outer and inner. So it's pretty similar to this one, but it might return a bit lesser contours. Yeah. So it will return those that are more well defined. And this one gives you all of the contours and reconstructs like how they are related to each other. So it sounds a bit abstract at this point in time. And it's okay. I mean, you can go and read out on the kind of mathematics behind it. But for today's purposes, we're just going to make use of the RETR tree. And then next, we're going to make use of some algorithm to kind of get all of the contour points. So yeah, you can read the summary over here. Yeah. It's quite complex. But yeah. So let's say if you were to kind of implement this in say a real world project, you might want to look closer into some of these details, especially if you want to optimize your like algorithm or you're like wondering why certain things are not detected, then you can probably look into some of the specifics of this. But if you're just gonna just test it out, then you don't need to like know all of them specifically. Yeah. Okay, so after that, next we're gonna sort the contours. So you might be wondering, what are lambda functions? So lambda function is actually this portion in functional programming. So what is functional programming? As its name suggests, it makes use of functions. So the idea is to kind of represent a lot of Pythonic like expressions. Instead of just adding them one by one, we create functions that can be reused. So basically the whole idea is having code that can be reused across tasks that are repetitive. So for instance here, let's say I have this array of values over here. Okay, in items, which is 3, 5, and 5. So what I want to do is I want to increment each element in the array. I can create a simple function called define add to array items, which takes in the array. And then I will use a for loop to kind of loop through all of the items in the array. So the range function basically gets you the this gets you the length of all the elements in the array, and then it loops through one by one, and then add them one by one. And then after that, I'll return the array. So from what I get is basically I increment every element in the array. So not very difficult, right? But I can also write this code in a much more simpler form using lambda functions. So in lambda functions, there's actually made out of three, in Python at least, there's three main implementations. The first one is map, second one is filter, and the other one is reduce. Yeah, map, filter, reduce. That's the three kind of it's a part of like functional programming. So we'll make use of map to kind of map a function object and a bunch of iterables. So the iterables, you can think of it as like the individual elements in each in the array lah. Okay. Which is, yeah, so how this works is I'll first have lambda. So this is the default for Python lah. Then after that, we'll create just any variable name. It can be X, it can be Y or anything, but I'll just use K. Then I'll use K and I'll map it to K plus 1. So, it's like you map the input and the output. So the input will be K and the output will be K plus 1. So this will be our lambda function. And then after that, we take in the second parameter items, which is the array above. Yeah. So this is like the iterable object that we can use lah. Then we'll make use of a map. But hold on. If I were just to use a map and I just print out this object, right? What I'll get is a map object 0x something 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 something. Then be like, why doesn't it like show my complete array? It's because this is by default, it's actually just a generator object. So what we need to do is to iterate over the generator object to print it out lah. So we make use of list function in Python. And then after that, it will print out everything. So you realize that the code is much, much shorter than the one above. Over here. It's a lot shorter. And so, yeah, so you realize this is kind of like a more efficient way of like writing stuff, writing code in Python. So you can consider using it when you implement certain complex things that are kind of reused in Python to keep your code more succinct. Okay. So going back to the worksheet. So I have this contours over here, right? What I need to do is make use of the lambda function to sort the thing. So I will use lambda x. So what this does is it takes in the contour area, which is the one at the top here. So it finds all the contour areas from X, and then after it puts them into the sorted, like in this array lah. So this basically produces an array that is in a reverse order lah. So it's descending order, yeah. Then once you're done with that, what we need to do is, let's say we have our camera rolling, okay? We are done with all of this code, the camera is rolling, and the image is appearing. But let's say if you don't see any object. Imagine if there are no red objects. In my room, it's just white, and there's no red objects. So we probably need to kind of handle this exception. So if let's say there are contours in the array, so that means the length of the array in this contour variable, it should be greater than 0 lah. Because if there are objects that are found that are red color, that means the array will be like, we have elements inside it, right? So of course it should be greater than 0 lah. So the length of the array, there should be elements inside, so greater than 0. Okay, and then after we'll create a bounding rectangle to kind of draw over the object. So we'll take in contours 0, which is the largest contour in the array. So imagine if it's a descending array, we'll take in the first object, which is the largest one. And then we will get the dimensions of the contour. So we'll get the xy as well as the width and the height of the object. Then after that, we will draw a rectangle. So actually, it doesn't need to be a rectangle lah. Like in CV2, if you see at the top over here, where is it? Here. Okay, let me wait for it to load. Yeah, you'll see that there's different drawing functions in CV2. There's circle, there's ellipse, there's a bunch of others. So, but we'll be using rectangle. So, anyways, then after that, the rectangle takes in a few parameters: the frame, which is the image, the video image, your XY, as well as your width and your height lah, basically. And then after that, this one is the initial coordinate. So this is like the base point, and then you add on the X and the Y, like the dimensions of the thing. Yeah. And then this one here, the third the fourth parameter takes in the color. So the color you specify it with, I think, BGR. So I'll just be having a green rectangle. So I'll just use this. Then this is the thickness of the rectangle. Yeah. The last parameter is the thickness of the rectangle. So if you want it to be thicker, you change 2 to like 5 or something. Yeah. Okay, but I want 2. So, okay. Then once you're done with this, you'll need to create a frame and the mask. Actually, you don't really need to show the original frame if you don't want. You can remove it. Yeah. Then after we have the wait key to kind of kill the program. And then make sure to release your resources and carry out all live windows once you have done. So, okay, then if you run it, give it some time to load, you should see that it isolates the object. Where is the mouse? Here it. You should see that it isolates the object. Yeah, with the rectangle. So it works pretty well even if it is near the thing. But you can see sometimes, right, when I bring it to the light, right, over here at the top, wait, alright, it sometimes catches on to the red object at the bottom there, over here. The red object over here. So you can really see it's really trying to pick onto the largest red object that it sees. So if you want to get more clarity, you bring up the mask. Then you can really see what is kind of picking up what's being isolated. So probably the colors that I chose just now not the best because it still picks up the window the side here, which is red. I mean not window, the ledge. Yeah. Okay, so that's it for color detection. Yeah, at this point in time, are there any questions? Oh, lambda again. Okay, sure. What we want to do next is you want to kind of isolate the largest contours, the ones that are most prevalent in the image, because we want to get the biggest object. I mean, if you want to get all of the objects also can, but for our purposes, we want to find the largest object. So we'll make use of a sorted function to kind of sort the array. Okay. So you will take in contours, which is the contours above over here, which after you find all the contours. And then we will use a lambda function, which maps the x, which is the iterable over the contours over here. And then after that, we will first we'll map it to like a contour area. So because you see over here x, right, it doesn't actually find the contour area. It finds the contours, but it doesn't tell you the contour area. So we need to calculate the contour area with the CV2 function. And we'll map x to the contour area so that it kind of calculates the contour area for each individual contour. Yeah. So that's the lambda function here. Then after that, we will put it in descending order. Yeah, is that okay? Now, okay, so we created something to kind of check your understanding. So it's just like a random. It's like the lucky com did the random thing. Yeah. So we will have some questions to ask you guys, and we'll just if you're lucky and your name is called, please unmute your mic and answer the question. Okay, congrats, Karen. What does NumPy Raro do?
Flatten it.
Yeah, correct. That's right. Convert it to you flatten it to a one dimension. Yeah. Okay, good job. Elliot. Hi. How many intensity values are there in a pixel?
3.
Okay, no. 3 is the different color spectrums. Like how many what's the intensity value? Like there's like 0 to something. Yeah. How many are there?
5.
I heard 255. Yeah, that's correct. Actually, it's 256 because you add 0 in as well because 0 is the first one. Yeah.
Oh, yeah, okay.
Okay, yeah. Good job. Okay, maybe I'll just ask one more person. Yeah. What does HSV stand for and why is it used?
I think it's hue, saturation, and value. It's
Okay.
it's just another way to represent RGB.
Okay. Okay, then now I'll pass the time to Emily.
Okay, Hello. So today I'll be going through Canny edge detection algorithm. So Canny edge detection, as its name already has something to do with edges. So edges is sort of like a boundary between the bookmarks bar over here and the website. This like, and the Canny edge detection algorithm is actually computer scientist John F. Canny in 1986. To give you like a quick overview of a quick illustration of Canny edge detection algorithm, I would like you all to see this particular picture over here. So this is actually a photo of Diamond High School in Singapore. Aside from just like a normal photo where you see all the buildings very clearly, etc., one very distinctive feature of this photo is that you see that its edges, the edges of the trees and the buildings, they have all been very clearly extracted out. So this is a very classic example of Canny edge detection algorithm where given an image or like a video, it can return you the processed image and video with very clearly defined edges. In popular like camera applications, you might take a photo of some landscape, like a selfie of your, and the application might prompt you to such. You just, for example, like this. Instead of just like a normal, you get just the edges of the cat bits. And aside from just these applications, you might often wonder what are the possible, what's the set of the next best possible move. For example, if I have a 8x8 chessboard with the corresponding chess pieces on it, and I take a photo of this board and supply it to the computer. So what it should tell me is the next best possible move. But how exactly will it do so? So for the first step, we must of course know where each of the 8x8 tiles are. And it's natural to assume definitely that there must be some kind of edge detection algorithm at play which can help us identify the which of the 8x8 like chess tiles are located at, so we know where are the corresponding chess pieces, and finally what is the best possible move after applying some set of algorithm. So even in popular like social media, for example, if you upload an image to Facebook will use some kind of image detection algorithm to extract out the faces within the photo. It can recommend you who in the photo. We find the intensity gradient is essentially figuring out where is the largest change in intensity of the image. And thirdly, so we filter out the local maximum and minimum values with a certain threshold. And lastly, hysteresis thresholding, where we determine which are the strong edges. So don't worry if all this sounds very complicated. And in truth, they're actually like very heavy in mathematics. So I will not bring you through like each of these 4 steps in detail, but rather I will just give you a brief view of all these steps so that when you apply the edge detection algorithm later on in the exercise, you have some sort of general intuition to know how it actually works. And in the application, in the exercise later on, we'll also be using the OpenCV library a lot from the previous presenters. OpenCV has language collection, computer vision algorithm, one of which being the Canny edge detection algorithm, which has like heavily optimized and for our usage and for performance. So in the first step, the Canny edge detection algorithm would perform like field, will apply the Gaussian field as to remove the noise in the image, because it's very hard to do image detection on a noisy image. A noisy image is when there's a random variation of brightness or color information. There's a lot of all these furs over here, and this fur can be considered as like noise in the image, which makes it very hard for us to get the edges. And to remove the noise in the image, we will use this function called the Gaussian blur. And the Gaussian function is an image, and it relies on uses this probability density function distributed variable. So if this for because you are to give you a quick overview. For example, if you see this particular curve over here, it has a very distinctive dumbbell shape. So this is actually the normal curve, and you realize that it's actually symmetrical about this vertical line. So this vertical line is actually the mean. The mean can be considered as like the average. For example, if I have 100 students and each of these students have like a respective weight of 50, 51, 55, etc. To find the mean weight, I would take the summation of all their weights divided by the number of students, which is 100. And the second parameter that defines the Gaussian function is variance. So variance will determine the spread of the data. For example, if I have a very large very large variance, it means that my data is very spread out. Therefore, I can imagine the curve to be flatter with a shorter peak. And if I have a very small variance, it means that my data is like very limited in range. So I can expect a curve with a sharper peak. And this method over here is the Gaussian, which is used to plot the particular Gaussian curve. And you might wonder what kind of scenarios we actually use this Gaussian curve. So it can represent a lot of things that are normally, such as the weight of the students or the height of the students. And in order to determine the probability that the Gaussian curve, the probability that the height of the student is of a particular value. For example, if the average height is like 160, and I want the probability that a student has a height of 155, I might be quick just say that we can just read off from this particular y-axis. But this is not, because in this normal curve, it's usually defined by an interval. And within this interval, there is like an infinite number of points on the curve. So it's not possible for us to mean the probability of one particular value. And in this case, it will just be 0. Because whenever we consider the probability, consider like the respective interval. We need to consider this respective interval. So instead, we might reframe the question to say like, what is the probability that a student has a height between 150 to 160? And in this case, the answer would just be the area under this particular curve. This like, so for each pixel, the Gaussian function will assign weight to the pixel and its surrounding pixel based on the Gaussian function. And the resulting weight will be based on the feedback from its neighbor. And you might wonder, what exactly is surrounding neighbors? What is the weight? And so to bring you through step by step, let us imagine like this image to be represented as n number of rows and n number of columns in a two-dimensional array. If we focus on just like one particular pixel over here, and we magnify the pixel, so this is this point considering just now. We have in right, top, bottom, and diagonal neighbors. And given like, and if we magnify out this particular section of the image, we can calculate like what is the resulting weight of this pixel based on feedback by its neighbor. So what I mean is that we can use this Gaussian function over here to give us a corresponding 3x3 array which defines the weight. And over here, this can be represented as having an xy coordinate of 0, 0. This can be thought of as having a xy coordinate of 1, 0. So similarly for the two-dimensional array of the pixel values, we can also think of this as having a xy coordinate of 0, 0. So what, and in each of these like array value over here is given by this Gaussian function. So to apply an image convolution technique, we can just take this corresponding weight at xy coordinate of 0, 0. Then we multiply it to the pixel value at 0, 0. Next, we take the weight at xy coordinate of 1, 0. Then we multiply it to the pixel value at 1, 0. And if you see where this pattern is going, we will continue this process for each the 9 pixel values. And finally, we can take the summation of all of these resulting weights and assign it to the final pixel over here. So in this case, this per here will have a resulting weight based on feedback from its surrounding neighbors. So this original pixel value will then receive the heaviest weight by having the highest Gaussian value, while the neighboring pixel will receive smaller weights as their distance to the original pixel increases, as you can see from this Gaussian curve. So this will result in a blur that will preserve the boundaries and edges better than the other, allowing for more uniform blurring filters. So the next step is to find the intensity gradient. So the gradient calculation steps will detect the edge intensity and direct by calculating the gradient of the image using edge detection operators. So for example, if you take a look at this picture over here, this blue curve is actually a plot of the pixel value simple image. And over here, where it's black, it has the lowest intensity. And where it is white, it has the highest intensity. This like in the middle of this particular curve has radius. Intensity change is the largest. But how do we exactly find out like that largest intensity change? We can gradient of this particular blue curve, and which is represented by this red color curve over here. And correspondingly, where the gradient is the steepest, largest intensity change. But how exactly do we do it in like programming? So again, if we consider the pixel earlier on, we can, which is, if we consider pixel earlier on, which is like this cross over here, and we define this 3x3 array consisting of surrounding neighbors, we can apply the same convolution technique by taking taking this particular value -1 multiplied by the xy coordinate at 0, 0, and we do so for all the remaining values in this gx array. And when we take the summation, we get the gradient of the pixel value in the x direction. And to repeat the same step, we'll apply the same convolution technique to find the gradient in the y direction. So in this case, we can get the magnitude as well as the orientation of the gradient. So to give you all a quick animation of how this actually works, for example, if you see this picture over here, I would like you to focus on this particular section, the selection, kernel, result, and change. So if you see here, the kernel is actually the 2D array for the gradient in the y direction. And if I focus on this particular section, you can see that by applying the kernel, I can get the change in the pixel value, change in the intensity value. So the next step will be non-maximum suppression, where we do a full scan of the image to remove any unwanted pixel which may not constitute an edge. So previously, the gradient calculation step will detect the edge intensity and direction by calculating the gradient of the image using edge detection operators. Right now, we are focusing to identify which actually are the true edges. Because edges correspond to a change of pixel intensity, we can easily apply filters that highlight this intensity change in both the x and y direction. And ideally, the final image should have thin edges. For example, if we look at this particular pixel here, like previous steps, we can count the orientation, which is exactly the pixel point. And so now we suppose that this pixel over here is pointing in the y direction. Then we can consider its corresponding neighbors in the y direction. If this pixel value have a higher intensity than its two neighbors, then we can keep this pixel. Else, for example, for this pixel here, if its intensity is less than the two corresponding neighbors, then we'll suppress this intensity to 0. In other words, decide this pixel an edge. And the last step will be versus thresholding. We find to an edge. So if you remember from the previous step, we identify out which are the possible edges. And now we want to differentiate the edges from each other by looking at which edges are the strong ones and which are the weak ones. So the strong pixels are those which have an intensity that are very high, such that we are sure they contribute to the final edge. Weak pixels are those which have an intensity value that is not enough to be considered as strong one, but they are not small enough to be considered as non-relevant for the edge detection. So now, after we have gone through these 4 steps of the Canny detection algorithm, we'll start to do a simple exercise which will let us apply the Canny detection algorithm on an image. Do you have the 4? Yeah, if y'all have the canny.py file, then y'all can react to the message. Or what I'm showing here is like a notebook file, which is easier for explanation. Okay, since some of y'all have prepared already, we'll first start off by downloading an image online. So of course, you don't need to download the image. You can also use your own image if you have one. So in this case, I will just download this particular like cartoon image, which I've gotten from the link. And now I'll give it a corresponding title, Tom and Jerry. Then I'll save it into my file. Okay, so now the output message tells me that I have saved the Tom and Jerry image successfully. So in your corresponding like Python file, you can just run this block of code before this line of hash sign to save the image. So the next step that we'll be doing is to import the relevant libraries. First is the CV2 library, and second is the matplotlib library. So the CV2 library is used for us to perform the Canny detection operation, and the matplotlib library is used to just display the original image as well as the final processed image to our like computer. So now we can just fill in the underline blanks by replacing the underline with like the library names that we are importing. So if y'all like have learned from the previous workshops, we use a AS sign over here so as to simplify so as to make it easier for us whenever we call the library. So instead of just cv2.caddy or matplotlib every time, we can just use a simpler reference name, plt. So after we have imported the library, the first step is to read the image data. So to read the image data, we can use the CV function, which is imread. And in the first parameter, we'll put in image file name, this variable, which contains the name of the image file that we are going to perform Canny detection algorithm on. So if you have like an image that you have loaded from your own laptop, you can also replace the img file name with the image name of your corresponding image. And the next parameter is 0, which means that we are just interested in getting a grayscale image. So the next step is to perform Canny detection algorithm. And surprisingly, in the CV library, Canny detection algorithm only comprises of one line of code. But in the CV library, they have like made it very optimized and efficient for our use. So we can just easily call this Canny method in order to perform Canny detection algorithm. So we can replace this to underline with the corresponding threshold. So I will leave. So this threshold is for the hysteresis procedure, where we find out which are the strong and weak pixels. So I will leave you all to figure out the threshold on your own with like different threshold. in the interest of time. So in the next task, after we have performed candidate detection algorithm, we would just like to display out the image. So for this, we'll just show the original image and we'll name the title of the plot original image. And then we will show. So this is the original image. And to get the image which has been processed before, we can just put in ages over here. And then in the PLT, we can call plt.title with a title of age image, and we call the show method. So in this case, you can see that the image has been like the ages has been extracted from this image. So it's quite different from the original image. We can also try changing like the threshold. And there are some noticeable differences in the ages that are being marked out. That's why I've come to the end of the Canny detection workshop.
By right, actually, thank you and give yourself a pat on the back, which is what the line we should be saying as we end the workshop. But we have one more thing that we would like to try out. Yes. So nowadays, right, face detection and face recognition is becoming more prevalent. Like, if let's say you unlock your laptop, for instance, you have Windows Hello for some laptops. So that kind of makes use of face recognition. But before you even recognize the face, you need to be able to detect that it is a face, right? So that's one of the big misconceptions people have between the two terms. So face detection is detecting the presence of a face, and face recognition is knowing whether the face is John, Alex, or someone else. Yeah. So that's the difference. So for face detection in Python, there is in the OpenCV library, they make use of this thing called Rilla-Jones framework. You can go read on it, it's quite interesting. But it does borrow some kind of concepts of the age detection that we've learned earlier. Yeah. Okay, so we're gonna now try and create a very quick program to kind of detect your face. Yes. I mean not your face, any face. So go over to your folder over there. Okay, and then create a new Python file. Yeah. So you can use your any IDE you want. I'll just be using idle. So yeah. Okay. So I create a new file. I'll just save it as. Save it. Raspberry card. No wait, no, wrong one. Okay, yeah. So I'll call it as right. Yeah, you can just call it face detection. Okay, so now I'm gonna be doing a bit of live coding, so try to follow along. Okay, so this time there's no worksheet. So but we think that since you guys have quite a lot of practice with the things, you roughly know what I'm gonna say next. So the first thing I'm gonna do is import the CV2 library. Yes. So we're gonna import the CV2 library, and then we're gonna capture a video from the laptop webcam. So and after that, we're gonna make use of a while true loop to make sure that it reads the image from the camera constantly. So from a while true loop, we are gonna read the image. So cap dot read, and it's gonna go into two parameters, which is one that is not very useful, and cap dot read. Okay, yeah. So this is kind of like the basis for quite a lot of CV2 programs. So you read from the image and you read And okay, so now we're going wondering how we're going to implement the face detection like algorithm. And here's the catch: you don't even need to implement it. Yes. So OpenCV right actually has a bunch of pre-built classifiers lah that that has all the necessary things that they basically train on all the different faces already. So you can automatically know when it's a face. So it's actually inside your OpenCV download folder. So if you go and search it up somewhere in your computer, which I went to do using this program called Everything, I found that it's somewhere in my program. As you can see, there's more than one version of it. There's so many different versions. Because, over time, if you download from different programs, you'll get all the different places where it is. So I found it in this folder. Okay, wait, no, not this folder. I found it in this folder. But because for today's purposes, for teaching a lesson, it's going to be very complex if I'm going to ask you to dig through all your folders to go and find this XML file. So what I'm going to do is I've already uploaded it to the Raspberry Pi folder. Go over to lesson files over here, and you will see the XML file over here. So I want you to right click and download it. Yeah, download into the same folder and transfer into the same folder as your Python program. Yeah. Once you have your classifier, what we need is we need to import the classifier from your system. So I'll create a variable called face cascade, which is equal to cv2.cascade classifier to kind of load the classifier. So there's if you go over to the directory, right? Okay, wait. Let's pause for a moment and just look at my com. Where is it? So if I went to the directory for the OpenCV, and you realize there's quite a lot of stuff. There's left eyes, license plates, and I don't know why there's Russian plate number, but yeah, there's quite a bunch of classifiers, pre-built classifiers. So you can go and experiment with them and see what they do after the workshop. Yes. This one detects your eyes, I think. Yeah. So yeah, okay, so we import the classifier. So it's car cascade. If you didn't change the name, it should be hard cascade frontal face alt.xml. Yeah, so this should be the name of your cascade classifier, and then you will go over and okay, then once you're done importing the face cascade, next we need to convert the grayscale image. So you'll be wondering why I need to convert the grayscale image. So the reason for this is this Viola-Jones framework, right? It works on having to detect edge features and these line features. And these features over here, they need the image to be of the same color scale. So it needs to be black. And then it needs to be variations of black and white to kind of detect the edges. So that's why we need to convert it to grayscale. Yeah. So to convert the grayscale, we'll make use of cv2.convert color, which will take in two parameters once again. Frame, which is the original frame image, and cv2.color bgr to gray. And we will convert to grayscale it is. So we will convert this to grayscale. Then after that, we will need to initialize the cascade classifier. So how you do this is you we will make use of this thing called face cascade detect multi-scale. So I'll just put it to a variable. And this face cascade detect multi-scale takes in a few parameters. So I'm just gonna copy paste it here. it basically takes in a few parameters. Actually not just these four lah. There's 4 more parameters, but basically it takes in an image, which is the image that we have converted to. So it'll be this gray color image, this variable here, and we also have a scale factor. So basically it will try and like how much it reduces the image size at like each time it detects the face. So yeah, there's a scale factor, but I'll just use a scale factor that the default one. And then next it also specifies like how many you can get specify how many neighbors each rectangle should have to like retain it. So like let's say you have an image and then you have different like faces. So how do you know like before you detect that it's the image, like how do you know how many rectangles like it should detect before everything is important? Cause if you think about it in this one, it's got something to do with this part over here. Yeah. And lastly is the minimum possible object size. So if let's say your face is too far away, then you probably don't want to if you don't want to detect a face that's very far away, then you can set a minimum size there. So yeah, so these are the different like values I'll be using. You can try with different values later on. Okay, so now that we have found all of the faces, right, we will need to get the individual dimensions of the faces. So I'll make use of a for loop to kind of run through all the faces that we get at each round, because it's a while through loop, right? So it'll be continuing like endlessly. So we'll need to, for each face that we find, we'll need to kind of draw a rectangle around it lah. Like a rectangle to show that I've detected the face. So we will make use of the CV2 rectangle function once again. So if you remember correctly, the CV2 rectangle just now took in about we used 5 parameters just now at the start, right? In the previous detecting of color. So it's the same thing. So this is the same thing. So the first parameter is the frame that we'll be using, the original frame. We can also use the grayscale frame theoretically, but we just want the original frame. And then we'll have x, y, which is the base coordinates of the face lah. This one is the width and the height. The color that I want, I'll use blue this time. And then I will make use of how thick you want your circle to be. I mean your rectangle to be. So I'll use 3. Then same thing. Once this will kind of identify all the faces already. So I just need to do the standard stuff to end the program as well as release the resources. So yes. Okay, sorry, I forgot this bit. Yeah, so you need to CV2 show the frame. Oh yes, correct. Thanks to Joe. Yeah, so I'll just give it a default name. And then I'll run it. Okay, yeah. So if you see over here, it should appear, and if you see my face, yes. So okay, yeah. So that's face detection. Yeah. So try out lah. Try out with the different settings and stuff. Yeah. There's many tutorials online if you want to try face recognition and stuff. So yeah. Thanks. So that's kind of the end of our workshop. But yeah, if you have any questions, can just ask.